Hey, it's Plumber Tom. Don't forget to check in the comments below for a link where you can find additional resources like practice tests and courses that you can take. Your support helps me to be able to create more great content. Thanks for watching. Hello and welcome to this presentation of the International Mechanical Code, Chapter 12, Hydronic Piping. My name is Thomas, and in this video we are going to pick it up in section 1204 and carry on through this chapter. Let's see what we can learn together about hydronic piping. You know what time it is. Get out your book, be ready to mark. Let's look at it together. Let's jump right into section 1204, which is titled Pipe Insulation. And let's consider for a minute the importance of insulating pipe. The whole point of a hydronic system is to try to transfer BTUs from a heat source like a boiler to a given location in the building. Along the way, if that pipe is not insulated, the pipe is going to be losing BTUs all along the way as that metal pipe or plastic pipe transfers heat into the space around it. The most efficient way to handle this then is to insulate the pipes and try to get the BTUs delivered exactly where we want them. Now, when it comes to the conservation of energy, the International Code Council has developed the International Energy Conservation Code, which dictates all things that relate to the conservation of energy. And interestingly, insulation of not only pipes, but insulation of buildings is all spelled out in the IECC. You'll want to be at least familiar with it to that extent. Now, again, when it comes to the conservation of energy, insulation goes a really long way. For example, if you have a building that is really well insulated on everything, the walls, the windows, the roof, the whole thing, and you have a really kind of like less efficient furnace or heating system, it's not going to be too inefficient because whatever heat it produces will be held within the building envelope, and the insulation can make the difference. So we see this principle, the importance of insulation if we want conservation. Let's look into the specifics. 1204.1 insulation characteristics. First of all, it has to conform to the IECC. That's the code we talked about. It has to have a maximum flame spread index of 25. Also, a smoke development index of not less than 450. And if pipes are run in a plenum, they can be insulated, but it refers us back to the Mechanical Code 602.2.1. Keep that in mind. 1204.2 talks about the required thickness. And this sends us once again to the International Energy Conservation Code for details. But we shouldn't leave this topic without focusing for a minute on the types of insulation that are available. That's right. If you're going to be installing a hydronic system, the insulation of those pipes has to be a part of your plan from the beginning. So let's look at insulation, some stuff you should know. First of all, there are several types of insulation that can be used. One of the most common is fiberglass. This is more rigid, and as you can imagine, it's quite uncomfortable when those fiberglass slivers get all over you, but it does insulate the pipe quite nicely. It is often used in steel mechanical or copper mechanical systems. Foam insulation is the other type. One of the advantages to the foam is that it's far more flexible and can turn and bend with plastic tubing better than fiberglass insulation. As we describe insulation, it's important to understand that there is an inside diameter and a wall thickness. The inside diameter should be the same outside diameter as the pipe that it would be applied to, so it'll fit nice and snug around the pipe. The wall thickness describes how thick the wall is from the pipe to the outside of the insulation. There are different wall thicknesses that you can get for pipe. When you are ordering insulation, it is important to describe both the pipe size and the wall thickness. If I were trying to insulate a 1¼ inch pipe and it requires a 1-inch wall, I would say I need 1¼ by 1-inch wall fiberglass insulation. It's important to understand that when you're ordering insulation, the sizes are different. Just like iron pipe is different than copper pipe sizes, you need iron pipe size insulation so that it will fit the outside of an iron pipe. Here is a table giving us the iron pipe sizes, the outside diameter, or the description. So we might say, I'm using a 3/4-inch pipe, but it's going to be 1 1/8. That's the inside diameter of the insulation. Easiest way to describe this when ordering would be to say, I need 3/4 iron pipe size by the wall thickness. Now again, the wall thickness could be a 1/2 inch or 1 inch. Those are the most common, but you can get it even thicker, 1½ inch, whatever. Here's an example of a copper tube size. If you're dealing with copper tubes or PEX, they have the same outside diameter and you're going to deal with a different sizing. For example, if I have a 1/2 inch pipe, I'm going to ask for a 5/8 insulation. 5/8 by the wall size. Let's talk about the installation of the insulation itself. If you're dealing with foam, you open it apart, slide it over the tubing, peel off the tape, and stick it back together. It's pretty simple. When installing fiberglass, you peel it open, wrap it around the pipe, peel off the tape exposing the adhesive, and lay the outside sleeve around and over the fiberglass insulation. This fully covers the fiberglass. Fiberglass insulation also has elbows. These are a PVC jacket, and fiberglass insulation is stuffed into that jacket or tucked in around the pipe, and then the jacket is applied. The jacket is held together with small stainless steel tacks, basically thumbtacks. You wrap the jacket and tack it to the insulation. Foam insulation elbows can also be purchased, but most professional insulation installers will just cut and trim the foam to fit. So there's ways that you can cut and wrap a pipe even for elbows and T's when you're dealing with foam. Fiberglass insulation also has T options. It's a similar PVC jacket. Fiberglass insulation is wrapped around the pipe and the jacket is applied over that. And then of course little thumbtacks are pushed in to hold that together. Foam insulation T's are also available. Now when it comes to the fiberglass, most of the time that is applied to larger mechanical systems, whether they're using steel or copper. These pipes are held by clevis hangers. Now, when you're supporting a pipe, you don't want to crush the insulation because that minimizes the insulating effect. So calcium silicate blocks are applied through the clevis hangers to be able to support the pipe and insulate the pipe. Here's an example of cast iron pipe that is being supported by clevis hangers with calcium blocks. You can see there's the blocks and then a stainless steel sleeve which protects the block by spreading out the pressure applied on that support right at the clevis hanger. It spreads that out over the whole block.
Gonna insulate the pipe. Fiberglass will make you itch, but you'll keep the heat inside, saving energy's a cinch.
Moving on to 1205, where we learn about valves. And of course, we're focusing on the installation of valves within a hydronic system. 1205.1 spells out where valves are required to be installed, and this is fairly logical. Anywhere that you want control.
We have to control the awesome and mighty power of water and gas pressures. Yeah. Now that's a pretty big task because you really must view pressurized water and pressurized gas as the twin monsters. No, I'm not even kidding. Look, tell me what happens. What happens if water gets out of control? Pressurized water gets out of control inside of a building. What does it do? It floods. It can cause tens of thousands of dollars in damages in seconds. What happens When natural gas gets out of control inside of a building, it can cause death and it can blow the building to pieces. So, you really must view these as the twin monsters of pressurized water and pressurized natural gas. And if you do that and have the proper respect for that, then you will also have an appreciation for valves and controls. And this is why they exist, so that we have plenty of control and we do not risk these wonderful conveniences and resources getting out where they should not. You know, ironically, it still happens. But you, as a plumber, want to be as far away from being responsible for a flood as possible. I'll see you on the next one.
Anywhere you want to be able to isolate a piece of equipment or a section of the pipes, you need valves, right? And because these are closed systems and they're circulating out and coming back, we have the supply and the return pipes in this looped system. You're going to see valves on both sides. If you want to isolate something, you're going to see two valves. Let's check it out. We're going to see valves on heat exchangers, central systems, pressure vessels, pressure-reduced vessels, equipment and appliances, expansion tanks. Let's start by looking at a heat exchanger. A heat exchanger is a piece of equipment that connects two separate parts of a system. You might have two closed loops, but we're trying to transfer heat from the boiler side from one loop into another. Now, this might be from the hydronic system to a potable water system, or it might be to a different part of the heating system at a different temperature level. There's different things we can do with heat exchangers, but look at this. How many valves do you see? For each side, supply and return, we're seeing separate valves, right? And unions so that we can easily disconnect this whole thing, replace the heat exchanger when necessary. We have control. It mentions central heating systems. What does that mean? That means we're talking like large scale. We're talking university campuses, separate buildings that are being heated by one central heating system. And this is common when it comes to a large campus, right? You'll have one central heating plant and a supply return, and then branches that go into the buildings. Of course, once again, we'd want isolation, valves that we can shut off each building without interrupting the entire system. 1205.1.3, anywhere that we would have a tank or a pressure vessel, we'd want to be able to isolate that. So we're going to have a valve at that tank. 1205.1.4, anywhere within this system, if we're going to have to reduce the pressure, we're going to want valves on either side of that. Now, that's not as common in the potable water system. We'll have a valve and a pressure-reducing valve, and then, it feeds the building. But in a mechanical system, we want more control. We want to be able to isolate. If we need to replace this pressure-reducing valve, which often happens over time, it's nice to have some valves on either side that we can shut off and replace that valve. 1205.1.5, anywhere that we have equipment or appliances, for example, before a pump, we'd want to be able to isolate that so that we can service or replace. And of course, expansion tanks. We would want to be able to isolate those as well, so valves for expansion tanks. 1205.2 talks about systems with reduced pressure. So if we have a pressure relief valve that's required on a lower pressure side of a system, we would want that to open up before we hit a high pressure or get above where it should be, right? So it says that pressure relief valve should be set at the maximum pressure of the system design. So if that system's designed for 25 psi, that pressure valve better open up anything more than 25 psi, right? We want it in the safe range at the maximum of the system pressure. Have a look with me now at section 1206, which is piping installation. That is a pretty broad topic, right? Because a hydronic system is a lot of piping installation. We're just going to look at a few things that apply directly to those systems in this section, but in general, this applies to piping, valves, fittings, connections, all of that. It says it has to be installed in accordance with conditions of approval. Yeah, that's pretty broad. But we're going to do it, right? You and I are professionals. We're great tradesmen. We value our quality of work. So yeah, we're going to do it right. Check it out. 1206.2 talks about system drain down. And this is something we have to think through in design. We may at times need to drain down this system, and it says hydronic piping system shall be designed and installed to permit the system to be drained. At a minimum, we have to figure out where are the low points, and let's put some valves there so that we can drain it down. So ideally, we find a good location where we can install a valve. A valve like this is a combination shutoff valve and drain valve. This is a 3-way valve. You can hook up a hose, drain it down. This is a great way to handle draining down a system. 1206.3 talks about protection of the potable water supply. Many times on a mechanical system, as we've discussed before, we're going to be using chemicals, glycol or other pipe-preserving chemicals, in those solutions that would not be good for us on our potable water side. At the same time, many times a hydronic system will have a direct pipe connection to the potable water system so that we can feed water into it if we need to fill it or refill it. So that pipe connection needs to be protected, or rather, the potable side should have one of these backflow preventers that will keep anything from pushing back into the potable system. For details on this, once again, we are referred to the International Plumbing Code, which dictates all things in Section 608 that we need to know for backflow prevention. 1206.4 talks about pipe penetrations. And whenever we penetrate through concrete, whether it's a wall or a floor, and we're moving hydronic pipes through there, we need to make sure there's a sleeve and that there's plenty of space around the pipe for it to expand and contract. Especially because we're dealing with heated pipes, they will be expanding and contracting. And we want to make sure there's plenty of room, not only for the pipe, but also for the insulation, so that the whole thing can move freely through that penetration. 1206.5 talks about clearances to combustibles. This is particularly for high temperature systems. It says if the exterior temperature exceeds 250 degrees Fahrenheit, you need to keep a 1-inch minimum clearance from combustibles. 1206.6 states that the hydronic piping system shall not be in direct contact with building materials that cause piping materials to degrade or corrode, or that interfere with the operation of the system. Basically, anytime we're passing through walls or other structures, we should have supports for our piping system on the pipe, but it shouldn't be touching directly any parts of the building structure. 1206.7. Let's talk for a minute about the important topic of hammer arresters. Yes, when water's moving through a pipe and it is suddenly stopped by a quick closing valve. A quick closing valve would be anything electronic, a solenoid valve that would suddenly close. That water's moving along with momentum. And when the valve closes, it hits a wall. Wham! Now inside of that, you have all of those water molecules that smash into each other and then bounce off the wall, and then they're bouncing back and forth inside that pipe because they're locked in and they still have momentum until it comes to a stop. Let's see what they have to say for this in the code commentary.
Yes, according to the International Mechanical Code commentary, the intent of this section is to protect the system and its components from the possible destructive forces that result from a rapid deceleration of fluid flow. Roar! Whoa, easy does it there, buddy. The rule of thumb is that the force or shock wave of the water hammer is approximately equal to 60 times the change in velocity of the fluid. For example, a quick closing valve can cause instantaneous pressures of 600 psi in a pipe with a flow velocity of 10 feet per second. If you ask me, that is a lot of pressure.
So, obviously, very important that where necessary, we install hammer arresters. Hammer arrestor can be something like this. It's installed in line with the pipe. has an air chamber inside that will compress when that water is stopped, and it gives somewhere for all that momentum to go. 1206.8 talks about steam piping pitch. When we have pipes that have steam in them, as they transfer steam along, some of that steam will condense back into a liquid as it loses BTUs. If that pipe is level, then that condensation is going to build up in the bottom of the pipe. That can become dangerous. So anytime that there are steam pipes, they do have to be sloped, similar to drainage. Not quite as much as drainage. It doesn't necessarily have to be 1/4 inch per foot, but there has to be some slope to that that's going to bring that condensate to a trap or a pocket where it can be disposed of or sent back to the boiler system. 1206.9 talks about stresses and strains. What we're dealing with on any hydronic system is the fact that you have hot water moving through pipes, and that is going to cause some stress, some strains, some expansion, some contraction. And as that is happening, if pipes are not allowed to move to some extent, then they can be damaged. They could rupture. This happens over time as there's that constant movement, expansion, and contraction. So what can we do about that? Well, this starts with the careful placement of our hangers and our supports, but it also involves strategic piping that allows for expansion and contraction. In the code commentary, we find this table giving us information about pipe expansion. In the left column, we are given a list of materials that can be used in a hydronic system. The second column gives us a coefficient of linear expansion. This is a proportioned amount that each type of pipe would expand. When the expansion of each type of pipe is applied to 100 feet at 100 degrees Fahrenheit, we see a certain amount of expansion in inches. Let's look at steel, for example. Steel is a common pipe used in hydronic systems. The coefficient for linear expansion is 0.000065. That may seem like a minuscule amount to you, but over 100 feet, it will expand to more than 3/4 of an inch. Copper is also commonly used in hydronic systems and has a similar linear expansion number, 0.000095, but it will expand more than an inch over 100 feet. What if you're using a plastic pipe? Say, for example, PEX tubing. Cross-linked polyethylene has a coefficient of linear expansion of 0.000078. That's a lot more than our metal pipes, and it would equate to an expansion of over 9 inches over 100 feet at 100 degrees Fahrenheit. Yikes, wow. So yeah, there is some real expansion that happens regardless of the type of pipe that you're using. Is going to stretch out when you heat it up. Now, what if you're pushing water that's over 100 degrees Fahrenheit? I would expect that these numbers for the distance that it will expand will increase. Of course it will. So what are we supposed to do about this? This is where we get strategic. Check this out. You can plan an L bend. Well, a lot of times we're going to have L bends in there anyway because we're just moving our pipes through the building, right? But if you set it up like this, with an anchor point on either end of the L, look at what can happen. That expansion can push out into that 90. This is a strategy that will allow for the expansion into that corner. Another option is the Z-bend. Once again, for an expansion, you're going to have 2 fixed points. Anchor to anchor expansion is what they call this. But in this case, we've put 2 L bends together. What's going to happen? Well, both of those are going to push out, allowing for the expansion of that section of this pipe. Notice that guides are installed. These are supports that are not anchored. They're not holding fast the pipe, but they allow it to push in and out or through that support or guide. And that allows for the whole thing to shift just enough to keep from major stresses or strains on any particular point. And we also have the U-type bend. This is where you use 490s and intentionally move that pipe out and back in from alignment. Once again, there are anchor points as well as guides that allow for this pipe to expand and contract. As it does so, it bends a little bit on those 90s. The idea is not that it's going to be so much that it would break those 90s, but it gives those pipes a little space to move. It may only need to move an inch or two if it's steel pipe, but if it's PEX, it might need several inches. Putting in these different types of bends allows for that expansion in a safe way. And that brings us to the very important topic of pipe supports. Hydronic involves a lot of piping, and all of that needs proper supports. If you want to know the proper spacing for supports, where do you go? Well, we talked about that clear back in Chapter 3 of the International Mechanical Code. So, this table 305.4, we have the listing of materials on the left column, the maximum horizontal spacing in the second column, and the third column has the maximum vertical spacing. At a minimum, I recommend that you know where this is at in your code book and that you know how to read it. But if you want to be a really efficient installer, then you should memorize the types of pipe and their spacing which you use most often. What ones would I recommend? For hydronic, I would recommend that you know about copper piping, CPVC, PEX, and steel pipe and tubing. All right, 1206.11, condensation. We've talked about hydronic systems and how often they are heating, but they can also be cooling systems. If we're using a fluid like a glycol to cool a building, we're still moving it around to transfer heat. Now we're just transferring heat from inside the building to the outside of the building. Because those pipes are going to be cooler than the rest of the building around it, it is very likely that moisture will condense on the outside of that pipe, especially in humid environments. So to protect that pipe from being wet and even eaten or eroded from the outside, we're going to insulate that. Now, this is also important because if water starts to condense on those pipes, it will drip. And if it drips onto other surfaces below it, it can ruin ceilings, walls, and floors because that water is just going to be running down on it. So we insulate pipes not only to keep the heat in, but to keep the moisture from condensing on the outside. Finally, let's look at 1207, transfer fluids. We may use any variety of solutions to transfer BTUs throughout a building to either heat or to cool it, but in any case, the flash point of a transfer fluid in a hydronic system shall be not less than 50 degrees Fahrenheit. Also, these fluids should be compatible with the makeup water or the potable water that is fed into the system. We don't want any wild chemical reactions here. And this concludes our presentation of the International Mechanical Code from Section 1204 to Section 1207. Join me in the next presentation where we will pick it up in 1208. We'll finish off Chapter 12 about hydronic piping. I'll see you there.